Look around and you'll see the same shape everywhere. Friends in a group, cities joined by roads, web pages linking to one another. Each is a set of things and connections between them, captured by one idea, a graph. The dots are called vertices or nodes. Here, 6 of them are through F. The lines joining them are called edges. Each edge says these two are directly connected. Watch the connections appear. That's the whole definition. A graph is a set of vertices plus a set of edges connecting them. We write it G equals V. E. V for the vertices, E for the edges. And a cousin you already know, a tree. A tree is simply a graph that's connected and has no cycles. Every tree is a graph, but most graphs are richer, with loops and many paths between points. Let's build the language on this very graph. I'll keep it on the right and point to each idea as it comes up. First, adjacent. Two vertices are adjacent if an edge joins them directly. A and B are adjacent. A and D are not no single edge between them. A path walks along edges from one vertex to another, never repeating a vertex. Here's a path from A to F, A, C, E, F, joined edge by edge. A cycle is a path that loops back to where it began. A, B, C, and back to form a triangle, a cycle of length 3. Exactly what trees forbid. This graph is connected. You can reach any vertex from any other. Split it into two pieces with no bridge, and it's disconnected. Two more words. A self-loop is an edge from a vertex to itself, and parallel edges join the same pair twice. Ours has neither. So it's a simple graph. Edges come in two flavors. An undirected edge is a two-way street. If A connects to B, then B connects to A. Mutual friendship, a two-way road. A directed edge is one way, an arrow. It points from one vertex to the other, not back. Think you follows V, or task you must finish before task V. Direction carries meaning. Edges can also carry a number, a weight. In a weighted graph, each edge has a value, a distance, a cost, a bandwidth. This A to B edge has weight 7. Unweighted graphs record who's connected to whom. Weighted graphs add how much, and that's what powers shortest route maps. For everything today, we'll keep it simple, undirected and unweighted, unless I say otherwise. Now a number for a single vertex. Its degree. Simply how many edges touch it. Let's count them on our graph. One vertex at a time. A has two edges, to B and to C, so degree 2. B reaches A, C and D, degree 3. C also has 3. D touches B and E, degree 2. E has 3. And F dangles off a single edge to E, degree 1. Now add all the degrees. 2, 3, 3, 2, 3, 1, 14. And the graph has 7 edges. 14 is exactly twice 7. No coincidence. This is the handshake lemma. The sum of all degrees always equals twice the number of edges. Why? Every edge has two ends, so it's counted once at each, twice in total. The same reason the total hand shaken at any party is always even. A graph in your head is fine, but a computer needs it in memory. The first way is an adjacency matrix. Keep the graph on the left. Let's build a grid on the right. Number the vertices A to F along both the rows and the columns, giving a 6 by 6 grid. The rule is simple. The entry in row I, column J, is 1 if there's an edge between them and 0 if there isn't. Start it all at 0. Take edge A, B, set row A, column B to 1, and because the graph is undirected, row B, column A becomes 1, 2. The matrix will be symmetric. Edge A, C. Light up A, C and CA. Edge BC, BC and CB. Edge B, D, B, D, and D, B. Edge C, E, C, E, and E, C. Edge D, E, D, E, and E, D. And edge E, F, E, F, and F, E. Every edge is now a pair of ones, mirrored across the diagonal. There it is. The full adjacency matrix. Notice the diagonal is all zeros. No vertex connects to itself. And flip it across that diagonal and nothing changes. Symmetric. The signature of an undirected graph. What does it cost? It always uses n-squared cells, whether the graph is packed or nearly empty, order n-squared space. But checking if two vertices are connected is instant. Read one cell, order one. Fast to query, but memory hungry. The second way is leaner, an adjacency list. Instead of a full grid, each vertex just keeps a list of its own neighbors. Read it straight off the picture. A's neighbors are B and C. B connects to A, C, and D. C to A, B and E. D to B and E. E to C, D and F. And F alone, just to E. Count the total entries. 2, 3, 3, 2, 3, 1, 14. Twice the 7 edges, just as the handshake lemma promised. Each edge shows up in two lists. The list space is order V plus E. It stores only the edges that exist. The trade-off. To check a connection, you scan one vertex's list. Order its degree. A little slower than the matrix. So which to pick? If the graph is dense, the matrix is fine, and lookups are fast. But most real networks are sparse. Far fewer edges than in squared. There, the list wins big on memory. Sparse graphs love lists. Storing a graph is half the job. The other half is exploring it, visiting every vertex in order. The first great method is breadth-first search. It explores in rings, level by level, using a queue. Pick a start, color it discovered, and drop it into the queue. Our to-do list of vertices waiting to be explored. Take a off the front and mark it visited. Its neighbors are B and C, both new, so color them and enqueue both. Front is B, visit it. Its undiscovered neighbor is D. Discover D, add it to the back. Front is C, visit it. Its new neighbor is E. Discover E, enqueue it. Front is D, visit it. All its neighbors are already discovered, so nothing new joins. Front is E, visit it. Its fresh neighbor is F. Discover F and enqueue it. Finally, F comes off the front. Visit it. No new neighbors. The queue is empty. Every vertex reached. Read the visited row. A, B, C, D, E, F. That's breadth first order. The start, then everything one step away, then two, then three. And its superpower. In an unweighted graph, breadth first search finds the shortest path, in fewest edges, from the start to every vertex. The other great traversal is depth first search, where breadth first fanned out in rings, depth first plunges. It follows one path as deep as it goes, and only backtracks at a dead end. It uses a stack, which is exactly what recursion gives you for free. Start at a mark it visited, and dive into its first neighbor. Go to B, visit it, and immediately dive deeper into B's first unvisited neighbor. From B we reach C, visit it, and keep going into C's neighbor E. Now E visit it, and dive again. E leads on to D. Reach D and visit it. Both its neighbors are already visited, a dead end. So we backtrack up to E, which still has an unexplored neighbor, F, down to F and visit it. It only connects to E already seen, another dead end. Backtrack all the way up. Every vertex is now visited. The depth first order is A, B, C, E, D, F. It charged all the way down before coming back. Breadth first spreads out, Depth first drills down. Same graph, two completely different journeys. Your turn. Same graph on the right. Two questions. 1. Write the degree of every vertex. 2. Give the breadth first order from A. Pause the video and work them out. I'll wait. Here are the degrees. A2, B3, C3, D2, E3, F1. They add to 14, twice the 7 edges. If your sum was 14, your degrees are consistent. And the breadth first order from a first, then B and C, then D and E, and finally F, A, B, C, D, E, F. If you got both, you've genuinely understood graphs, degrees, and traversal. Well done. Trap 1, the big one. Direction matters. In a directed graph, an edge from U to V does not give you V to U, and its matrix is generally not symmetric. If it is symmetric when the graph is directed, something's wrong. Trap 2. The adjacency matrix always eats n squared memory, even with a handful of edges. For a large sparse network, that's huge waste. Use a list instead. Trap 3. Breadth first runs on a queue, depth first on a stack, or recursion. Swap the structure and you change the entire visit order. The structure is the algorithm. And trap 4. A single traversal only reaches vertices connected to your start. If the graph is disconnected, loop over every vertex and launch a fresh search from any still unvisited, or you'll silently miss whole pieces. Let's lock it in. A graph is vertices joined by edges. G equals V. E edges can be directed or undirected, weighted or not, and those choices change everything. The degree of a vertex counts the edges touching it, and the handshake lemma ties it together. The degrees always sum to twice the number of edges. You store a graph two ways. The adjacency matrix, order n squared space with instant lookups. The adjacency list, order V plus E, linear, the natural choice for sparse graphs. And you explore it two ways. Breadth first sweeps outward in rings with a queue and hands you shortest paths. Depth first dives deep with a stack. Master these, the vocabulary, the two representations, the two traversals, and you're ready for the graph algorithms coming next.